we're not going to talk about standard deviation. It's a very important concept. You'll hear about it in statistics and probably other courses as well. Very closely related to the ideas we've been looking at. We'll look at it in the context of vectors and considering vectors collections of numbers. Okay, so if I have a vector x, it's an n vector. The average of the vector is the average of the entries. So it's 1 transpose x, sorry, inner product of 1 and x, which you now recognize as the sum of the entries in x, and then divided by n. So that's the average. So it tells you what the average of the coefficients is. Okay, now d-mean vector. Oh, and I should say that that's not standard. No, that's not universally accepted standard notation. So, I mean, someone would probably figure out what it means if you wrote this down, but just to let you know. Okay, and then the idea of a d-mean vector is very interesting. It says you take the vector x and you subtract the mean value from each entry of it. That's called the d-meaned vector. We're going to denote that as x tilde, and it's x minus the average of x, that's a number, which is the average value of the entries, times 1s. That's the vector of all 1s, all entries 1. So the average value of x tilde is 0, right? Because you've subtracted the average and so on. This allows us to talk about what the standard deviation is. The standard deviation is nothing more than the RMS value of the d-meaned vector. And if you want to write it out in all its glory, it looks like this. It's x minus inner product of 1 and x divided by n. You'll recognize this part here as the average value times 1s. That's when you multiply a vector times 1s, you get a vector with all entries equal to this number, the average. And it says subtract that from x and then take the norm, then divide by square root n, which gives you the RMS value. That's the so-called standard deviation. And what it is, it's a measure of the typical amount by which xi varies from its average. So if I have these x's and the standard deviation is 2.6, it says that whatever the mean is, let's suppose the mean is 7, it says we would expect the entries to range between from if the mean is 5, it would go up to 7, 8, 9, and down to 2 or 3. But you wouldn't have numbers that were crazy. It would be around that average value. Okay, and the typical deviation would be this standard deviation. Now, a vector has standard deviation 0. Let's see what that means. What it means is that this is 0, this quantity up here. That only happens if x is equal to its average times 1s. And that means x is constant. So a constant vector means it's a multiple of the 1s vector. That means all the entries are always the same. And that has standard deviation 0. And that's perfectly interpretable. Because if I give you a vector, all of whose entries are the same, and I say, how much do they typically vary from the mean value? The answer is they're identical. All of them are identical to the mean value. So they don't vary at all. So that kind of makes sense. That's what it means to have standard deviation 0. Now, just as a side note, very common ways to denote the mean and standard deviation are the Greek letters mu and sigma, and I guess they stand for mean, mu, and sigma stands for standard deviation. Okay, so that's and these are also very widely used across applied mathematics, probability, statistics, and other areas. Okay, now there's a basic formula relating the different quantities we have, and that's this. It's that the RMS value of a vector squared is equal to the average of the vector squared plus the standard deviation squared. Now, I'm not going to show that formula, although it's a pretty quick derivation, but I don't know. You probably don't want to see me doing some algebra on my little pad here. But it's actually a good thing for you to try to show yourself. It's a great exercise. And you'll use a couple of the properties of the inner product there to show that. Okay. Now, this comes up, it's at the heart of a lot of quantitative finance. So let's see what that is. Let's suppose that X is a time series of returns. And it means in each period, did a dollar of investment go up, in which, or did it go down, that kind of thing. And so it's just a time series of returns on some investment. over some period, right? So, well, over n periods, I should say, because each entry is going to be a return in a certain time period. Okay, so that's what it is. And so, let's suppose it's. I mean, it doesn't matter, but it's going to look like this. Let's say it looks like this. It's you know, 0.05 minus 0.03, 0.11, and minus 0.2. That's a lot. Okay, well, too bad. I already wrote it. All right, here it is. So this is what it says. This says in the first period you made 5%. Well, that's okay. That's decent. In the next period you lost 3%. In the next period you made 11%. That's like great. That's awesome. And then unfortunately on the next step you lost 20%. Okay, so this is an example of a time series of returns. Okay. Now, if I take the average, then what I get is the mean return of that asset or investment. That's the mean return. And it's the mean return per period, right? So usually those are converted to annual, but it's just what it means, the mean return per period. Okay. And that's usually often just called the return, right? So I'd say, what was the return of that, over the last year? And somebody would tell me, daily. Okay. Now, standard deviation of a return time series, super interesting. It tells you basically, typically, how much did the return deviate from the average, right? So, for example, if it looked like this, 0.01, 0.001, whoop, and all the entries are 0.01, it's awesome. You'd say, what was the mean return? You go, 1%. And you go, what was the standard deviation? And the answer is 0. And so we interpret that as sort of risk. It means that you were guaranteed to make, whatever it was, 1% in each time period. That was never higher, it was never lower. So this is actually referred to as just the risk, the standard deviation of the return time series. And what you do is you'll usually compare these. This is how you compare different time series. They have to be, this is how you compare different time series. So you would say, my portfolio made, over that time period, it had an average return of 12%, let's say per year. And I had a standard deviation of 10%. Okay. So, and we can interpret that means that we should not be surprised if the return in any one period would be certainly plus or minus, the people would say it is 1 sigma. That would be the slang. So you'd say, so we should hardly be surprised. So we might have a year in there where we did 25%. We might also have one where we lost money. That's a negative number. So, okay. And then these are often plotted on a risk return plot. Okay. So, which gives you the two attributes of a return time series. Okay. So here's an example. I guess I've got 10, maybe this is 10 periods. Yeah, this is 10 periods. And here are my returns. Okay, so this one, what is that? That's like the tortoise or something. Okay, so here's the tortoise. And it's boring. You get a return of 1. I don't know what it is, 1%. It doesn't, the units don't matter. It's just a steady return. It's, the average is 1 and the standard deviation is 0. So in fact, what people would then say is something like it's riskless. There's no, it just every year it's the same. There's no question of what it's going to be. Now this one, that's kind of interesting. Let's look at that return time series. It says that in the first time period, let's say you made 5%. You're laughing at the person who had this other investment because you say I just made a return 5 times what you made. Okay. On the next period, you make about 1, right? That's this one. And then on the third period here, you'll lose money, right? So, and then I guess at that point, this one's laughing and saying, I'm always making 1%, but I've never lost money. I'm not going to lose money. Anyway, okay. Here's another one over here, another one. And, your eyeball sees that some of these C's are even larger, more extreme. So your eyeball at least tells you that maybe the risk or standard deviation is higher. And here's a final one, D. And we can almost see that D is bad visually, right? Because for example, in the first 4 periods, you lose money. The return is negative. You lose. Okay. Then all of a sudden you make a bunch. Then you lose again twice. Then you make a bunch more. And okay. So if you work out what the mean of these are and the standard deviation, which refers to risk, return and risk, respectively. Now we plot them, right? And so that would look like this. This is a very famous plot in finance. That's the mean return there, and that is the risk. And just to give you the rough idea, although this is not part of that now, it's just to show you that the concepts we have, like standard deviation, come up in real things. In this case, in finance. So I mean, it should be kind of obvious that we like high return, right? I'd rather make 5% than 2%, and I would prefer that to losing 2%. So okay, so up the mean axis is good, right? For risk, people generally prefer it to be smaller. In other words, if you could do something like that, that would be perfect, right? That would be that's one measure of risk. There's actually a lot of measures of risk, but the truth is, this is the one that's actually used most often. Okay, so that's the risk, and there, small is good. So here, right? So here's where you want to be on a risk return plot. You want to be in the upper left corner. Upper means high return. Left means it was on a corner. You want to be on the upper left side. Left means you did it with low risk. So that's what you want. You want high return, low risk. Okay, and those are just these 2 attributes. And so for these 4 return sequences, we can see a couple of things. A comes out over here. It's got 0 risk because it just doesn't. It's constant. It's a constant all the time. Here's B. Sure enough, look at that. It's got a higher return, like 2 and a bit times as much as the first investment, A. But its risk is higher too, and that's here. C has a higher return and higher risk still, and D over here is it's kind of a sad thing, right? It's got about that investment has only a little tiny bit more return than A, but A has 0 risk and D has 4 units of risk. So okay, so by this thing we don't like D. Interesting question. We'll come to it later. By the way, is this which of these is best? It's an interesting question, and the answer is we can't say. Actually, there is something we can say. If we like return to be high and risk to be small, this is correct, then it turns out you can't say if A or B or C is better. You can't say which one is better. It depends on what people would say is your risk appetite. If someone said, yeah, yes, I'll take 2.5 times the return for a risk of 2, I can do that. And so, that's completely subjective. It depends on the actual investor. But we can say something. We can say that D is simply that's a bad one. Why? Because look, here's A, which gets about the same return, but has 0 risk as opposed to whatever 4 units of risk, right? So the name for something like that is, let's see. The name for that is, you would say it is dominated by the others. Right, so it is dominated by the investments, A, B, and C. But basically, it's crappy. That's the technical term for what the investment D is. Okay, so this is just to tell you that standard deviation, mean, these are kind of the staples of quantitative finance. So the Chebychev inequality can be transposed to talk about standard deviation. And there, it's very interesting, and this is something you should just remember, like, period. This is the right way to remember the Chebychev inequality, in my opinion. So suppose you have an n vector, x. It's got an average, which is just average of x, and standard deviation, which is standard of x. Okay. Now, the rough idea is that the entries, average of x is sort of like the middle point or whatever. It's a typical value, right? The standard deviation tells you how much the entries, are above and below the average. So what this says is, if you would like to know, this is what fraction of the entries are away from the average by alpha standard deviations. That's how people would say this. that is no more than 1 over alpha squared. That's what it means. That's for alpha bigger than 1. I mean, it holds for alpha less than 1, but it's not interesting. Okay. Now, here's a very specific example. Is for any return time series with a mean of 8% and a standard deviation of 3%, a loss, and that responds to xi being less than or equal to 0, that can occur no more than 3/8 squared, which is about 14% of the periods. That's it. So that tells you that. By the way, it's just a Chebychev inequality, but you kind of get the idea. And so the way people think of that in their head is roughly something like this. Most entries of the vector are between plus and minus, 1 standard deviation, 1.5 standard, 2 standard deviations. That's kind of. Now, by the way, if you have had a course on probability, don't confuse this with like a normal approximation or something, which gives you something different, right? This is the Chebychev. This inequality has nothing to do with probability or distributions or anything.